Welcome to an introduction to Earth science. I am your professor, Dave Cocchiarella, and of course we'll be working out of the textbook Foundations of Earth Science, written by Lutgens and Tarbuck from Pearson Education. It is the 8th edition, and in this textbook, they have an introduction. Many textbooks, maybe even all textbooks, have introductions. Oftentimes, it's just where the author thanks people or gives credit where credit is due. This introduction actually talks about Earth science in a meaningful way, and so I do want to cover some of the content, some of the topics that it did cover. So I guess the first question is, Earth science, what is it? Well, Earth science is the name for all sciences that seek to understand Earth, but also its neighbors in space. And we're not just talking about Venus and Mars, we're talking about the entire solar system, plus the entire area of space that the sun has any impact on. So we're really talking about a fairly large area when we study Earth science, the other parts of space that we're going to study. The components of Earth science are the sciences of geology, oceanography, meteorology, and also astronomy, but they're not separate components. They all interact together as one massive system. So when we study geology, we're not only studying physical geology like rocks and minerals and earthquakes and volcanoes, but we're also studying historical geology, which gives us the history of Earth, the 4.6 billion years or 4,600 million years that scientists believe Earth has been in existence. Oceanography integrates many sciences because there's chemistry, there's physics, there's geology, and there's biology, all part of oceanography. And of course, all those aspects of oceanography also interact with the other components of Earth science, of geology, meteorology, and astronomy. Of course, meteorology is the atmosphere and processes that actually produce weather and climate. And you don't have meteorology without oceanography and the interaction between the atmosphere and the ocean. And astronomy as well, because everything on Earth is driven by one of two processes, internal or external. Those external processes are going to be the sun, specifically. The sun and gravity, and those internal processes, the heat of the Earth and the heat of radioactive decay. So astronomy is very important, understanding the sun and how the sun impacts the Earth, very critical to the study of Earth science. And of course, when we go back to the history of the Earth, the study of the universe, the origins of the universe, the origins of the solar system, and the origins of Earth. All right, so one of the most interesting, personally interesting aspects of Earth science is this concept of geologic time. And geologic time is simply the span of time since the Earth's formation. But it's one of those things we need to understand because as humans, the construct of geologic time is very difficult to wrap our minds around. Just how long 4,600 million years is. I mean, this semester may seem long to you, so certainly the whole year is going to be a long period of time. And then 5 years or 10 years, or maybe even, I can even imagine 100 years, that's longer than most lifetimes. Certainly can't imagine really 1,000 years, or 10,000, or even 100,000, but you need 10 of those 100,000s just to get a million, and then you need 4,600, not just 1,000 millions, but 4,600 millions to get the span of time that Earth has been in existence. So we look at Earth as something that's been around for 4.6 billion years, and so if we take that 4.6 billion years and we compress it into an Earth's single year, we get an idea of what that looks like. So the origin of the Earth was on January 1st. The 12th of February, the oldest rocks. Late March was the first evidence of life, not like life like squirrels and rabbits, but like bacteria, single cell life. Then mid-November, so now we go all the way through to mid-November before we get to the beginning of the Phanerozoic eon, which is animals that actually had hard parts. That's after the Cambrian explosion. That's mid-November, so you have to get to late November before any plants or animals move on to land. So the entire span of the Earth is in one calendar year. You're in late November before any plants or animals show up. Then it's December 15th to the 26th is when the dinosaurs dominate, right? And we move to December 31st, the last day of the year. All the times are going to be PM. They're not, this is not in the morning. So it's a minute and 15 seconds before midnight when the Ice Age glaciers pull away from the Great Lakes. And then it's 11:49 before any humans are in existence. And it's 11:59:45 before Rome rules the Western world. And you can see how this progresses. The bottom line is Geologic time is a massive thing. Not only are we dealing with massive scales of time, we're dealing with massive and minute scales of space. So earth science examines phenomenons from the size of the atom to the size of the universe, the entirety of the universe. So we go from the atom to minerals. Atoms make up minerals, atoms make up elements, elements make up minerals, minerals make up rocks, rocks make up mountains, mountains and continents make up the Earth's part of the solar system. Of course, the solar system is part of the galaxy, and as we know now, literally billions and billions of galaxies making up the universe. So Earth science and all of Earth science is all about integrated systems, lots of systems having an impact on one another. Our environment, the environment we live in, is highly integrated and never dominated by a single phenomenon, but characterized by the interactions of all of Earth's four spheres, which is, you know, hydrosphere, atmosphere, biosphere, and the geosphere. So the hydrosphere is this dynamic mass of water that's constantly moving. It's evaporating, it's condensing, it's precipitating, it's flowing, moving either over water or through the ground. And the hydrosphere is this whole dynamic mass of water. We no longer think of the Atlantic Ocean as being an ocean and the Pacific Ocean as being an ocean. We think about the world ocean and the world water. And when we look at the hydrosphere, 96.5% of that is salt water. So when we say salt water, we're not just talking about salt as in salt that you can taste. We're talking about all the salts that make up the ocean. This salt's referring to all the different ions, different minerals that might be there. Sure, there's sodium and chloride, which make up salt, but there's other minerals as well. So salts is everything that's been put into fresh water through erosion and the dissolution of rocks, or the dissolving of rocks. That's what puts salts into the water. So fresh water is only 2.5% of all water on Earth, and then about 69–70% of all fresh water is locked up in glaciers. There's a small amount that's in groundwater, and even a smaller amount that's actually on the surface, liquid water that we can see, and a very small amount that's actually in the atmosphere. Speaking of the atmosphere, the Earth is surrounded by a very shallow. Our atmosphere is extremely shallow, even though it's a life-giving envelope of air we call the atmosphere. It provides the air that we breathe, but it also protects us from solar radiation, meaning not all of the sun's radiation is good, right? When you go to the beach, you put on a sunscreen, and what you're trying to do with that sun protection factor 50 is to protect yourself from the UV rays of the sun. The UV rays of the sun are those rays that will burn. They have high energy. They carry high energy. They're very short wavelength. They carry high energy. That's why they're ultraviolet. They have a very short wavelength, lots of energy. Well, if the atmosphere wasn't there, nothing could be on Earth, particularly because you wouldn't have oxygen to breathe, but even plants, because UV rays would be so powerful they would scorch whatever's at the surface. And that's the way the Earth was for many hundreds of millions of years before the rise of oxygen and to create ozone to block out the UV rays of the sun, or most of the UV rays of the sun. Nothing can live on land. So the atmosphere not only provides us with the air that we breathe, it also provides us with solar radiation, and it provides us largely from the space debris that makes it onto the top of the atmosphere. All right. The constant energy interactions between the atmosphere, the surface, and space is what produces weather and climate. So a couple of things to look at here. Here is the surface of the Earth to really the edge of space, and that top of the troposphere. The troposphere represents the top of the layer of the atmosphere in which active weather exists. And the top of the troposphere is this extraordinarily thin layer. And when we talk about all the air in the atmosphere, gravity pulls most of that air very close to the surface. And because of that, in terms of the molecules of air, carbon dioxide, oxygen, nitrogen, hydrogen, whatever else oxygen molecules may be making up the air, the constituents of air, most of those molecules are pulled to the surface. So literally half of those molecules lie below this altitude of about 5,000 meters. And then as you go up, the number of air molecules in the atmosphere become fewer and fewer and fewer. Remember, when we talk about climbing up a mountain, we know it's harder to run around the top of a mountain than it is to run around down here at sea level, because what do we say? We say the air is thinner up there. There are literally fewer air molecules as you go up in elevation. Most of those air molecules are pulled and clustered at the surface. All right, the biosphere includes all life on Earth and in the oceans. And you know, most life is in a very thin layer at the surface or the sunlit layer of the ocean, but there are other extreme organisms that live either very, very deep down in the hot rocks or very, very deep down at ocean vents. So most of life is right at the surface, but not all of life. All right, the geosphere extends from the surface of the planet to the core of the planet, to the center of the Earth. It is the largest of the Earth's spheres, and it's layered. So the Earth is layered. It's layered due to density differences, and it's also layered due to chemical composition. So there's different ways that we layer the Earth. Typically, what we've learned through middle school is that the Earth has got the core, the mantle, and the very, very thin crust. But we also know that the inner core is solid, and because of pressure and temperature differences, the outer core is liquid. And that's extremely important because this outer core actually spins around the inner core a little bit more quickly than the inner core spins. And that differential in the different parts of the outer core being liquid, iron and nickel, so all metallic, and the solid inner core actually creates the magnetic field. That's that differential in the liquid going around the solid more quickly literally creates the magnetic field, and the magnetic field of the Earth is what protects the Earth's thin envelope of atmosphere from solar radiation, from the solar wind just stripping it away. So it's a very important aspect of the Earth. The second layer is the mantle. That's that's high density rock. The core is even the highest density rock, and then the crust is a much lower density rock. Again, so on the left side of the cross section shows that there are differences based on chemistry, meaning the chemistry of the core is iron and nickel, the chemistry of the mantle is a high-density rock, and the chemistry of the crust is a low-density rock. And then there's also, on the right side, we're going to talk about layers based on factors as to whether we have liquid, solid, weak, or strong. So we have that liquid inner core. So all of the core is iron and nickel. That's a chemical property. But the inner core is solid, the outer core is liquid, and then most of the lower mantle is solid. But when we get to the upper mantle, because of temperature and pressure differences, the upper mantle is actually solid, but it's mobile, it's plastic. It can be moved like warm candle wax. And then the this gray upper layer of the mantle, because of temperature and pressure differences, is actually solid. And that very thin upper layer of the mantle is actually stuck to the crust, which is, is solid, whether it's oceanic crust or continental crust. So that crust, whether oceanic or continental, is stuck to this very thin upper part of the mantle, and those two together are called the lithosphere, all right? But this upper part of the mantle that is not solid, but is actually mobile, is known as the asthenosphere. And what we'll learn when we talk about tectonics, the grand unifying theory of geology, is that this rigid lithospheric crust and a mantle moves along on top of this mobile asthenosphere. So the rigid lithosphere moves along on top of the asthenosphere, and that's how the plates move in plate tectonics. And again, plate tectonics pretty much explains most aspects of geology, and that's why they call it the grand unifying theory of geology. So the Earth is a system. It has a nearly endless array of subsystems that are constantly interacting with each other, and those subsystems all are recycling matter. And then sometimes you could even think of recycling energy, but in the end, recycling matter over and over and over. The parts of the Earth system are linked so that a change in one creates a change in the other. 120 years ago, scientists were geologists, they were meteorologists, and they were separate. Now we know that all these different studies interact together, and if we separate them, we have a smaller volume of knowledge than if we bring them all together. The Earth system, as I said, powered by two sources. The sun powers the external processes, but you also kind of have to add gravity in there when you consider things like mass wasting and waves. But nonetheless, the sun powers external processes that occur in the atmosphere and the hydrosphere at the Earth's surface. And the heat, two places that heat comes from, remaining from the formation of the planet and from radioactive decay, that powers the internal processes that produce plate tectonics, mountain building, earthquakes, and volcanoes. So environment is anything that surrounds and influences an organism. The physical environment encompasses water, air, soil, rock, as well as the conditions of temperature, humidity, and sunlight. And those physical aspects of the environment are sometimes referred to as limiting. Like If it's too hot, certain plants can't live. If it's too cold, certain plants can't live. So humidity and the amount of sunlight, like some plants like sun, some plants don't. So there can be limiting factors in the environment. Resources, as you know, water, soil, minerals, energy, can be renewable or non-renewable. Renewable resources can be replenished over a short period of time, like plants and animals, even forest products like trees. Also, what can be renewed easily is water flowing from or energy flowing from wind or water and sunlight. Non-renewable resources require millions of years to replenish. They include, of course, the metals, natural gas, and oil. So the introduction kind of wraps up with this concept of the nature of scientific inquiry. This is essentially the scientific method, and the most important aspect of science, I'll tell you right off the bat, is science is only good science if it can change when new information comes about. Meaning, we thought that the world was flat, then we had new observations and new information that told us that the world was round. If you couldn't change your opinions from flat to round, you weren't a good scientist. We thought that the Earth was the center of the universe, and then several scientists, the last of which being Galileo, made observations and determined that we're not the center of the universe. We're moving around the sun. And those that couldn't accept those new information, that new empirical evidence, and change their way of thinking, that was bad scientists. Good or bad science. Good science is when new information comes in, you're able to accept that new information, empirical evidence comes in, and change your way of thinking. So that is the key to science, that new information changes what we know. I always think about the last part of Men in Black, when yesterday the one character told the other, yesterday we thought we were alone in the universe, today there's aliens living on Earth. Imagine what we'll know tomorrow. Imagine what we'll know tomorrow. That is the key to science. So all science is based on the assumption that the natural world, the world we live in, behaves in a consistent and predictable manner that is understandable through careful systematic study. The careful systematic study, that's the science. New scientific knowledge is developed through universally accepted logical processes, meaning they don't do science different in Europe or Asia than we do them in the Americas. It's all universal. The scientific method is a process in which data is gathered through observation. Okay, that's the empirical observations that you made, whether you're observing something, whether you're measuring something, whether you're using models to come up with new information. That's the observations, the empirical evidence. Those observations about questions you might have, like why does the sun always come up in the east? That's a question. So you make observations, you formulate a hypothesis. Well, my hypothesis is that the Earth rotates counterclockwise if you look down from the top. So that's a good hypothesis. And how can you test that hypothesis? Well, you can wait every morning and see where the sun comes up. And when it comes up every morning in the east, that supports your hypothesis. And eventually, with enough people supporting that hypothesis and agreeing, it becomes a theory. So a hypothesis is a tentative explanation of a natural phenomenon. The sun comes up every morning in the east. To be accepted, the hypothesis must pass objective testing and analysis. And that means lots of people have to be able to do those tests in lots of different places and come up with the same solutions. If you're the only one that ever did the test to prove the Earth is hollow and there's people living inside of it, if no one else can do that test, then no matter what evidence you think you have, it's no good. A hypothesis must pass objective testing and analysis done independently. When a hypothesis has survived extensive scrutiny, then it possibly becomes a theory. A theory is a well-tested and widely accepted view explaining certain observable facts. The sun comes up in the east every morning. Those are the observable facts. Well, the theory is that we're spinning counterclockwise in the solar system. And that's how it becomes a theory. And you see, we don't have law like the law of gravity because we really don't make laws. Laws are unchanging in nature. And even gravity, as much as Newton understood it to be, and he came up with a great formula to describe it, which is quite accurate, even gravity was changed when Einstein began to talk about relativity and the bending of space and time by massive objects. So very rarely do we now have laws. So the last part of our conversation in the introduction to the textbook about scientific inquiry are the specific steps to the scientific method. Of course, you watch what's happening in the world around you and you have some questions about it. So the first part of the scientific method is to raise those questions about the natural world. Then you go and you do some research, you collect some data, you make some observations that relate to the question that you have. From there, you construct that hypothesis. That is supposed to answer the question, why does the sun come up every morning over there in the east? And you make the observations, and your hypothesis is the sun is at the center of the solar system, and we are rotating, and therefore the sun comes up in the east every morning. Now, you've constructed that hypothesis, you develop additional observations and or experiments to test that hypothesis. So maybe your experiment is, I'm going to stay up every night and see whether the sun comes up in the east. And you perform those experiments, you analyze the data. Today it came up in the east, yesterday it came up in the east, the day before that. Okay, so you have results that now support your hypothesis. You then share those results, the hypothesis and the results, with the scientific community. They will go out and conduct the same experiments or conduct similar experiments and see if their findings support the hypothesis. Now, if your data doesn't support your hypothesis, then you have to go back and try again and collect more information and construct a new hypothesis. But it's only when we go through the scientific method and that everyone all across the world can recreate your experiment and come up with the same answers that a hypothesis is supported. If somebody else's experiment comes up with a whole new set of data or new observations, your hypothesis may have to be changed. And that's kind of what I said at the beginning of this conversation, that science is only good and only good science if you can change your hypothesis or even your theory with the development of new observations or new data. So that is going to wrap up the introduction to Foundations of Earth Science, the 8th edition by Lutgens and Tarbuck. And again, this is the textbook for our class, Introduction to Earth Science. Next up is going to be Chapter 1, and we'll see you then.